Good afternoon, students. Today we are going to see about the GP Thomson experiment. Yes, this experiment is to carried out to confirm the matter waves. Yes, de Broglie waves. De Broglie waves are nothing but light has a dual nature, both particle nature and the wave nature. To confirm this de Broglie waves, we are doing this experiment. The first experiment is the Davison-Germer experiment by using a diffraction crystal as a diffraction plane. We calculated the lambda value and it is more or less equal with the theoretical and the experimental value. Yes, the next one is the P Thomson experiment. This is also to confirm the matter waves. Yes, P Thomson exhibited a wave nature of high energetic electrons. Yes, his arrangement is shown here. His arrangement is shown here. The electrons are produced from a heated filament F and it is accelerated. Here it is the filament F. It acts as a cathode and accelerated through a high positive potential given to the anode. Yes, we are having a filament and to this filament it is passed through the cathode and the high energetic accelerated electrons are passing through the high positive potential and given to the anode. Yes, the whole apparatus is kept in a evacuated chamber. Why it is should be evacuated? Already I said that if we have a pressure inside this vessel, what happens that these electrons will not move directly towards the anode. It will be deviated. Yes, so to avoid these deviations, the movement of electrons somewhere else collision will be takes place. To avoid all those things, first we had to evacuate the pressure inside the chamber by using a rotary oil pump or a mercury diffusion pump. After evacuation only we have to start the experiment. So for now first the filament is heated, then from the electrons are coming out. These electrons are passed through the slit and it moves towards the anode. And these electron beam passed through a fine hole with the metal blocks B and falls on the gold foil G. Yes, or this gold foil is around thickness of 10 to the power minus 8 meter. The electrons passing through the foil are received on a photographic plate. The foil consists of a very large number of microscopic crystals oriented at random. Yes, therefore, some of them are always the correct angles to give rise to a central spot and it will be equal to the Bragg's formula 2d sin theta equal to n lambda. Hence, on processing the plate, a central spot marking the position of undeflected electrons and surrounded by a series of concentric diffraction rings. Yes, so the first direct spot is the central spot and around which then deflected concentric diffraction rings will be obtained. Yes, if we study this photographic plate, from this we can study the ring conformation. Then we have to find out the first order diffracted rays makes an angle theta. What are all the rays which makes the first order diffracted angle with an angle of theta? Then it is easy to calculate from the Bragg's formula 2d sin theta equal to n lambda. Where if we consider theta, sin theta is very small, then from the interplanar spacing we can easily calculate the value d value. So see, this is the central spot and with the around this we have the first order diffraction pattern. So by measuring the distance we can easily calculate the value. So from all those things it is the comparison of d obtained in this will be very agreed with the values determined from the X-rays of known wavelength. Yes, this is for if we use the X-rays of known wavelength, it is easy to calculate compare the d values. For example, in a case of gold foil, the value obtained by the above formula, this is the formula. So we can above formula, then we can easily formulate it and the value is calculated as 4.08 for a gold foil. And if we use the X-rays to determine this by this method, it is around 4.06 Armstrong. Yes, it is very well equal with this de Broglie waves, conformational de Broglie waves from the Bragg's law and from the photographic first order concentrated rings. Thank you, students.